Thank you very much, and good afternoon. Statement to say that I'm delighted to welcome all of you to the President's distinguished lecture today. I am delighted in so many different ways, but I'd like to take this opportunity in the audience, a surprisingly large number of students, alumni, and special guests who have joined us today to hear today's presentation by Dr. Stanley Whittingham about lithium batteries and what the future holds for the battery technology. I thought in order to underscore, to highlight the importance of the lecture today, I would ask the audience a couple of questions. How many people in the audience have electric vehicles? A few. Are there people in the audience who happen to have a smartphone? How about anybody who has a laptop? Anybody have an electric toothbrush? Anybody, I guess I should not ask this, but I will anyway. Hearing aids, maybe? And so many other things that utilize batteries. The reason I ask this question is for all of us to reflect for a moment about life without batteries. Life without batteries would be a miserable experience. And advancement in batteries could pave the way for significant technological and societal changes in so many different domains. So that makes me particularly pleased about the topic of our lecture today. And of course, it gives me special pleasure that I have the opportunity to introduce the father of lithium batteries to all of you. But to set the context, I should say, for more than a decade, the President's Distinguished Lecture Series has created the platform for some of the most influential scientists, technologists, policymakers, and business leaders of our time who have come to Stevens and discussed topics ranging from science and technology policy to national security, to future energy systems, to fracking technologies, to cancer research, to artificial intelligence, and so many more. Past lectures have included the director of the White House Office of Science and Technology Policy, the former chairman of Intel, the director of research at Google, a Nobel Prize winner who had led the National Cancer Institute and the Sloan Kettering Organization, among many others. These talks have elucidated our knowledge of technological advancements that are shaping the 21st century society. Today, for the 18th installment of the President's Distinguished Lecture Series, we are delighted to welcome Dr. Stanley Whittingham, Distinguished Professor of Chemistry and Material Science and Engineering at Binghamton University, where he's been for, I understand, 35 years, to share his insights on the need to advance lithium battery technology beyond its current limitations and to explore viable alternatives to build sustainable infrastructure. Dr. Whittingham, I and the audience, we can't wait to hear what you're about to share with us. Dr. Whittingham was the 2019 Chemistry Nobel Laureate for the discovery of lithium rechargeable batteries, and also the 2023 VinFuture's $3 million grand prize winner. I don't know if that was taxable or not, but congratulations to you. He is a member of the National Academy of Engineering and Fellow of the Royal Society. He presently leads the Battery NY $113 million economic development effort and is the Chief Innovation Officer of the recently awarded NSF Upstate New York Energy Storage Engine. He is a founding member of the New York Battery and Energy Storage Technology Consortium and serves on the board as Vice Chair for Research. He also serves as Chief Scientific Officer of the National Alliance for Advanced Transportation Batteries. He received a knighthood, so he's actually a knight in the King's Birthday Honors 2024 list. I can go on and on for a long time to talk about the achievements and accolades that Dr. Whittingham has received, but I will not because I'll be taking time from his lecture. All I would say is that following his Doctor of Philosophy at Oxford University, Dr. Whittingham was a research associate in materials science and engineering at Stanford University, which was followed by 16 years in the energy industry before returning back to academia at Binghamton University. He developed the materials chemistry programs and subsequently master's and doctoral degrees in materials science and engineering. He actually, for a while, went to the dark side and served as Binghamton's vice provost for research for 5 years, and as vice chair of the board of directors of the Research Foundation of the State University of New York, SUNY. Please fasten your seatbelts for a fantastic lecture and join me in welcoming Dr. Whittingham. Thank you very much, Dr. Whittingham.
Thank you. So is my mic on? Yes?
Yes.
Good. So what I want to do is give you a bit of a history lesson, show you where I came from, why New Jersey is important in my life, and really where we're going to. But two things I want to do is first thank US Department of Energy. They've supported my work since about 1993. So for a very long time, and I encourage all young faculty members, if somebody says, write a proposal, do it. I was in Japan on a JSPS fellowship at the time. My secretary sent me a fax. Remember, we had fax machines then, no emails. Said, this grant proposal is due in tomorrow. Can you do it? So I sat down that night, handwritten the whole thing, faxed it back to her. And she sent it in. 6 months later, we got our first part of DOE money, and we've been going strong with them ever since. The Department of Energy has been a great supporter of my work, and I'm sorry to say they're under slight stress at the moment. We'll see what's really going to happen in the future. But the key message I want to give, read what the Nobel Prize said. The comments I give at talks now, we talk enough. We've got to now do things, make things happen. Okay. So a little bit about my history, just in case any of you don't know. I went to Stanford School, which is about 100 miles north of London. This was what we call a semi-private school, but the state paid for my tuition there. And I studied in high school chemistry and physics, so some of the students asked me, how is US and UK different? By the time you finish high school in Britain, you've done the first 2 years of college in the US. So when you go to college, you study one subject. I studied just chemistry. And then those days, a little bit of German, because all the databases in chemistry were in German. Nowadays, everything's switched and it's easy. Everybody speaks English everywhere. So I went to Oxford. Oxford in those days had 3 chemistry departments: inorganic, physical, and organic. Inorganic included metallurgy and what we now know as material science with inorganic. Material scientists here will maybe remember the Hume-Rothery rules. He was the one who taught me my metallurgy and material science. He had an office right next to my lab. I then did a bit of organic chemistry one summer, working on paraquat, which is a weed killer. We found a new way of making it, and I gather it's on the dirty list right now. It doesn't do all nice things. Then at Oxford, your 4th year, you have to do full-time research. And I did my research looking at how oxygen atoms recombined on some metallic surfaces. Because those old, if you remember, Russia got the rocket up first, so there was panic in the US. So it's the US Air Force in London who paid basically for that research. So that was one lucky step. Then I got funded by the Gas Council of Britain to look at catalysts to convert coal gas into natural gas. I got the award, I think, in May or June. That August, they struck natural gas in the North Sea. I got a letter from them saying, you got your award, you got it for 3 years, we don't care what you do, just give you a copy of the thesis at the end. So I freed them for 3 years. So we looked at how some of these same oxides react. So my whole career has been looking at really how ions move inside solids. Okay. And this fellow here is Peter Dickens. He was my advisor at Oxford. He was one who really got me interested. And I expect if you ask any of the students here, why are they in the disciplines they are now? There's somebody in their high school or college that got them excited. Having been in England all my life, most folks, they want a good academic job or a good industry job in the UK, had to spend 2 years in the US at that time. And I said, if I'm coming to the US, I'm going to leave the rain behind, and if I can get to California, I'm going. So I went to Stanford University there to work with Bob Huggins, and I, in the end, spent 4 years there because after a year, I got married. I applied for the green card, and I was very lucky the university applied for me. In those days, they had to guarantee my employment until I got it. So those were good times. And again, I was looking at how ions moved in solids. And this structure, this white one here, is a compound called beta alumina. Ford Motor Company discovered that sodium ions moved as fast as in that solid as in aqueous solutions. So it's very exciting. They were thinking of making batteries out of it. So we studied how fast those ions moved and how they moved. And the Oxford work involved this other compound. You see lots of holes there, atoms again moving through those solids. So that was the interest. Then when I finished at Stanford, both Bell Labs and what was then ESO were recruiting heavily scientists, and Ted Jabal, who was a Stanford Applied Physics faculty member but worked at Bell Labs every summer, recruited, I think, about 4 or 5 of us who went to ESO, and 4 or 5 who went to Bell Labs. For those of you who are too young to, ESO had their research labs 10, 15 miles south of here, Linden, New Jersey, right across from the refinery. And that's where we did all the battery work and a whole lot of other stuff. Those were great days where we got involved in everything in the company. And the company was really looking 10 years into the future, not just tomorrow. Okay. And ESO really wanted to be the Bell Labs of the energy industry. That was their goal. So we worked on batteries, fuel cells. Exxon was the largest manufacturer of solar cells in the United States at that time. Okay. So they got involved in anything. And the last time I visited this campus, we think it was about 40 years ago. The campus has changed a lot, but Hoboken's changed even more. We used to have the New York Metropolitan section of the Electrochemical Society used to have its monthly meetings right here, not in this building. Then in Exxon, I rose to be division manager of chemical engineering, and I said, I prefer doing research. I prefer working with younger folks. So I said, time to go back to academia. So I went to Binghamton. I was the first materials person on the faculty. We quickly found out students liked materials, so we had a materials chemistry track in chemistry. That was so popular that we then set up a materials science and engineering PhD programs and MS programs, and those are still very active today. So let me thank again ESO for all the work they've done. That was me just a few years ago, okay? And that's the structure of our cathode titanium disulfide. The point at the bottom are single crystals of titanium disulfide. And I'll come back to that a little bit later. And that's a copy of the original patent we got. So we made the very first lithium-ion rechargeable batteries in Linden. And as they were commercializing it, they had a few fires, but not on operating batteries. When batteries don't work well, you pull them apart. Every one they pulled apart burst into flames. So we learned there are issues there. At the top right-hand side is a paperweight we used to give away to potential customers. So it has a battery in there, a little solar cell and a little clock. And that particular one is still in my house. We think it was built about 1976. So this one's almost 50 years old and it's still working. So a well-made battery works forever. We can never afford to make a battery like that today because that has ceramic seals in it and all sorts of things. Beneath that is one of the batteries we made for powering electric cars. Yes, Exxon wanted to make electric cars. Remember, there weren't any computers, laptops, phones, or anything. Electric cars was their goal. And this is about 6 inches by 4 inches, about an inch thick. And it was the largest lithium batteries till about 10 years ago. So these are very large. And even then, we drove this to Chicago for the electric vehicle show. But literally we had these sat on a desk just like that so people could come and look at them. Particularly the ladies will notice this looks like a pressure cooker. Has these little pressure release valves. So every night when everybody left, we'd release these valves, let the gas out, because the particular electrolyte we're using wasn't particularly stable. But that's where we were then. This is a few years later. These are some early applications of lithium-ion batteries. These are all in Broome County where Binghamton is. The one on the left-hand side there is an 8 megawatt system. We think it's about 2 megawatt hours. This was just across the river from the university, right next to a coal peaker plant. They turned this on, and 2 months later, the coal power plant was turned off forever. So a small battery can replace a peaker power plant. We had a huge flood in Binghamton in 2011. This floated. They fixed it. It went to Ohio for 1 or 2 years for the grid service there. And right now then, it moved to Puerto Rico after the 2 huge hurricanes they have to stabilize the grid. So this is a very old system, still working. And this is what utilities like about lithium-ion batteries. You see these are typical containers. You can pull up a truck to them and move them within a day's notice to some other place. On the right-hand side is a module from a BAE Systems bus. These were also made, and this particular one was made in the oldest and largest wooden building east of the Mississippi until it got washed out in 2011. So this is one taken out of a commercial bus, and we keep it as a demonstration. Thousands of little cells. And that's still what Tesla uses, little cells like this. So that story's what about transportation? A series of pictures here. Raymond forklift trucks. They're made in our county as well. Raymond is a division of Toyota. So these are high-end forklift trucks used a lot by Amazon in their warehouses. Beneath that is one of these BAE Systems buses. The little car there is my wife and I. We rented this one for our 50th anniversary. To those who have been to Bermuda, you're not allowed to drive cars there. They changed the rules. You could drive electric vehicles. So we drove this one for 1 day. It was about the 3rd car on the island. They warned us when we drive it to take it to the other end of the island, make sure you recharge it. It won't get back. So we took it to the far end of the island, drove to the recharging station. They were still building it. So fortunately, we found a hotel on the way back where we could plug it in, get enough power in as we ate dinner, and then we managed to get it back. But my wife still won't have an electric vehicle because there's range anxiety. So some of the other typical EVs. This is a 16-wheeler, top there, from Pacor. A garbage truck. These were at Pacor's test track, which is north of Seattle. I got to drive these around their test track. And believe me, this 16-wheeler truck has about 2 tons of concrete in the back to stabilize it. Get up to 60 miles an hour with no trouble at all. The only comment they say is, please don't go up on the banking around the corners. And the garbage truck is clear. This is a beautiful use of batteries. You're stopping and starting up and down all day long. So I think they're selling a lot of these. The truck itself is in the LA docks right now, moving containers to distribution sites. And at the bottom are 4 London buses. London Transport is testing out the next generation. The big one there is a fuel cell bus. The top one of the 2 is an electric bus. Below that is a hybrid. Then this one on the right they claim is a clean diesel. And I'm not quite sure what that means. But when I went back more recently, they're going more hybrid than anything else right now. And this is what clearly, us in the Northeast with cold weather, we're going to go hybrid more than pure electric. So let's look at where we've gone in grid storage since that first one in Binghamton. Clearly, renewable energy, it's intermittent. We've got to have storage. And this is even the case if you get a large new nuclear plant, and New York State is planning to build some. Those operate at constant output. You won't need that much power all the time, so you're going to store it in. So I've already mentioned the Binghamton one. The one at the bottom there, to put it in perspective, is 3.3 gigawatt hours. This is by far the largest in the world at the present time. And it sits in the Mojave Desert. So everybody's very happy. There's no one who lives within miles of it, unlike the one they built near San Francisco. And the big issue in California, solar energy has negative value in the middle of the day. So they'll, in fact, pay you to take their electricity. So this is what these grid storage units are doing. They're storing the energy in the middle of the day, then dispensing it in the evening. Those are just 2 major applications. Another one, maybe not so familiar with, when we're in Sweden for the Nobel Prize ceremony, 2 of the physicists and myself talked to these 2 astronauts on the International Space Station, and it was just like talking to you. I talked, they responded immediately. It was amazing. And the lady is of Swedish descent. That's why she's got the Swedish flag and the American flag. He's from Italy, and they just finished replacing the old nickel metal hydrides on the International Space Station by lithium ion. So the lithium ion's half the weight, half the volume, and we're going to last twice as long. So they're happy. And they were the ones who installed most of those batteries themselves on the outside of the space station. Now, I have to show this slide because somebody in this audience who doesn't know what a lithium-ion battery is. And just to show there are 3 real components. On the left-hand side, that's what we call the anode. That's where the lithium is. Where it's fully charged, all the lithium sits on that side. On the right-hand side is the oxidant. And when you discharge it, the lithium runs across and reacts with these various materials. And in between is the electrolyte. If you remember your lead-acid battery, that's the acid in the middle. This is what we call intercalation reactions. In other words, the lithium goes into these materials between those sheets without changing the crystal structure at all. So if you put it in and take it back out, the structure should look exactly the same. And if you've got a very old dictionary at home, look up the word intercalation. It'll refer to February the 29th. You intercalate it into the calendar every 4th year, then you take it back out and the calendar is back to where it was. So this is what we've been working on, a lot of work on every component of it. So we started out in '72. We licensed the technology when Exxon got out of it to a number of companies. One of them was Everready. Turns out Everready was working with Sony in Japan at that time. So the technology got transferred to Sony, and Sony was the ones who really willing to put 10 years worth of engineering into it to make it a commercially viable product. Lithium-ion batteries were being sold in the US prior to that, but no one made any money. Sony made money because they're vertically integrated. and their little Walkmans and everything else, they made everything in that, including the battery. So they developed the lithium-ion battery. And while we started out, the anode was pure metallic lithium. Okay. Then we switched to lithium aluminum alloys because lithium makes dendrites, and some people have noticed that. That's what creates some of the fires. Then Akira Yoshino then said, lithium aluminum isn't all that good. We can cycle it half a dozen times. He then worked on carbon, which is what I show you here. So these are the sheets of graphite. If you've got a lead pencil, that's what lands up on your piece of paper, those sheets of carbon. Okay? So the lithium goes in and out of the carbon. That is incredibly weight and volume intensive. So it works very well, but it restricts the energy density we can have in the batteries. So we're now trying to go back to lithium, and we're using as an intermediary things like tin and silicon that react with 4 atoms each of lithium. So if you're in the semiconductor business, the worst enemy they have is lithium, because lithium reacts with everything. So they want to keep it away. So this is the anode side. The cathode side, we work with titanium disulfide. And that's the picture here. Layered structure, works exceptionally well, but its energy density is fairly low. So John Goodenough, who was at Oxford at the time, was working on cobalt oxide for its magnetic behavior, saw our paper and said, hey, my compound has a strange structure. It should work. Now, at B1, any self-respecting chemist knew it wouldn't work, because you take lithium out of this compound, you've got cobalt 4+. Cobalt 4+ doesn't exist. John didn't know that, so he just did it. And it worked. Okay. But there's a message here. Almost all the battery materials we use are thermodynamically metastable at some state. So if you get this compound, take the lithium out, then you warm it up, it will fall apart. And this is one of the dangers of these compounds. They're unstable, so they can release oxygen, and that's the oxygen that can cause fires. Cobalt's too expensive, so nowadays we use a mixture of nickel, manganese, and cobalt, NMC, or Tesla uses nickel, cobalt, and aluminum. All very expensive, so a big pushback now to go to lower cost materials, and it was John Goodenough again who discovered that lithium iron phosphate, a common mineral, would work. You can get lithium in and out of that. Very poor energy density. So a lot of us are now trying to improve it by putting manganese in there instead. Or as we're doing in our lab, we're trying to put 2 lithium ions in to make up for the low energy. And I promise I'm not going to show you much chemistry today. Okay. So that's where we are. Huge incentive, better anode, better cathode, and we want a better electrolyte in between. So really we want to change everything. Ignore all the numbers in here, okay? Just look at what's inside the red oval. This is the percentage of the theoretical volumetric energy density that is in commercial cells. So this lithium iron phosphate getting about 15%. The very best commercial ones are 25%. So 75% of the volume of your battery is dead weight, dead volume. Similarly, if you on the right-hand side, 75% is dead weight as well. Okay. So a huge incentive. Can we reduce this dead weight and make them much better? So we have a very large consortium funded by DOE whose whole goal is to get from this 250, you'll see here 260, 250, which is 25%, trying to double that to get that to 500 watt-hours per kilogram. And again, so I'm not going to get into the chemistry here, but these are the cathode materials, what we call meatballs. Now, so small primary particles, these all agglomerate to get into larger ones, and this is what they use, and quite often a variation of sizes so they pack better. Okay, but that's what we use. Don't worry about all the numbers on here. This is a 5-year, our first 5 years of this program. In the year 1, 2017, we could recharge this material 50 times and get 300 watt-hours per kilogram. Remember, commercial was 250. A year later, we got up to 250 cycles, so we said, let's increase the energy density, push it harder. So we got up to 350 in 2019, and today we're up to about 1,000 cycles at 350. So we can increase the energy density of these materials. We are using pure lithium metal, not the safest thing. We're going back to the old Exxon electrolytes, the ether-based electrolytes, because they plate out lithium better. So everything's gone full circle. So this is the typical layered structure. So what's happening today is everything's moving forward, the energy density is going up, the costs are clearly coming down, and we'll get back into that later in the talk. Just some more recent data. I can show this because we've published it. As soon as we get to 350 watt-hours per kilogram, we're under export control regulations. So we can't tell you how we do it. We can show you the data once it's published. So here we're at 400 watt-hours per kilogram. We're getting about 250, 300 cycles. And we have, in fact, most recently got up to 500 watt-hours per kilogram. Our original goal, we got about 60 or 70 cycles. But in all these cases, now we have to improve each component and make sure the system is safe. And I should emphasize this is a large consortium. It is now mostly led by Jay, who is my ex-PhD student. She's was at Pacific Northwest National Lab. She's now at the University of Washington 50% of the time. And for the students here, I think I told some of you earlier, I have 3 chemistry PhD students who are all now full tenured professors in mechanical engineering departments. So this is how this field is. This whole battery energy storage field is really materials. And I keep promoting to my president and others, we should get rid of some of these boundaries at the graduate level, because really all the actions is interdisciplinary research these days. So we're making, I think, great progress here. We're now writing the renewal for the next 5 years. We're told by our inside informants at DOE this program has high priority, but we'll see what happens in the next 6 months. So going back to one of the big issues, I mentioned these materials are metastable. They want to release oxygen. The more surface you've got, the more reactive they are. So ideally, you want 0 surface area, but then you won't get any reaction. So on the top left-hand side here is titanium disulfide, large single crystals. These are up to 1 millimeter on the side and probably 100 microns thick. Beneath that is the original Sony materials, cobalt oxide. They went for as large crystals as they could to make their systems safe. And then what happened, we wanted power. So we went to these meatballs, high surface area, and now there's a big pushback to go back to single crystals. And this is a lot of research going on. These single crystals were made by Aizixu in my lab. She stays now at Argonne. She just recently moved to UL to continue this work. So single crystals, less surface area, less reactive. And according to Jeff Don, if you do this right, these batteries could last 1 million miles. No one realistically is ever going to drive 1 million miles. What it means is you can tie your car to the utility grid at all times where it's not moving. So your utility can take power from your battery, put power in to stabilize the grid, and hopefully they will pay enough for that so your car costs go to 0. But this is important in local regions, particularly important after disasters, where maybe your car can keep your house going for several days. The Ford Lightning truck allows this without voiding the warranty. I'm not sure any other vehicles do in the US yet, but I know colleagues who do that. The chemistry challenges is how to make these in tonnage quantities, these single crystals. We're working on it, and clearly the Chinese are rushing us ahead as fast as they can. And if we keep these crystals below about 3 microns, they don't crack. So what do I mean by cracking? I'll show you in 2 slides, but just show you these single crystals. Here's the capacity. cycle it 150 times, there's no loss of capacity. So single crystals work. The question is, can we make it economic? So what we found out, the other way we can protect these materials so they don't react with everything that we don't want the reactions, is to do what you all do. You've got a car, you paint it so it doesn't rust. So what we do with these meatballs, if we add 1% niobium to them, put a coating on them, this stops the cracking, and you see on the left-hand side there, this NMC 9055 means 90% nickel, 5% manganese, 5% cobalt. You get these large cracks in it. One on to the right has about 1% niobium, little cracks that don't give you any problems, but no large cracks. And you can see over on here, we've got 300 charge and discharges with no loss of capacity. So no, we can do it. Our challenge right now is, can we make tons of this material? So now we're working with Argonne National Labs to make initially kilograms of it. So if you can do that, then we can get commercial. And the folks in Brazil are very happy. They have about 90% of the niobium market. So they're pushing hard for success here. So let me emphasize, before I switch off the technical stuff, there are many options here. We started out with titanium disulfide. The Canadians in Vancouver switched to moly disulfide, same structure, because that mineral is available in British Columbia. You can just dig it out of the ground and use it. That went commercial for a while. Then we went to lithium cobalt oxide. That's John Goodenough's, and NiMnCoAl. Then we went to the olivine, this lithium iron phosphate, and that's the structure I showed you here. You'll notice this is the three-dimensional structure, no longer layers. So it's much more stable. It does not evolve oxygen. Doesn't lose any capacity as you cycle it, but too low energy density. So we're working on these, what we call vanadial phosphates. For the chemists here, they all know vanadium, go from vanadium 5 to vanadium 3, so you can put 2 lithiums in. The others, you can do one oxidation state. So this is a low-cost, stable cathode. The big push, and I'll keep mentioning this, it's available here. It's available in Europe. Cobalt is not here. Nickel is not here in enough quantities. So this is something we can build and make. So what are the real issues we worry about? And this is the kind of thing I'm spending most of my time on these days. To make a lithium-ion battery, it takes between 40 and 80 kilowatt hours of energy to make a 1 kilowatt hour battery. This is from the mine to the finished product. And I think it was Elon Musk who talked about this poor little nickel atom has to travel 50,000 miles before you really use it. That has to change. No, that's not sustainable. So what we really need is what we call secure, localized supply chain. So each continent really needs to supply all the minerals it's going to use. The other thing we have to do, which is what's happening, we have to stop building new old gigafactories. So we're getting gigafactories built all over the world using technology that's 20 years old. So what we're trying to do is leapfrog the present manufacturing process. And if you've seen how they make batteries, you make electrodes, you make a paste, then you paint it on copper foil or aluminum foil. Use this organic chemical NMP to make that paste. It's toxic, and takes up about 40% of the total energy consumed in the plant. Because once you put it in, you've got to cook it off. So what we're looking at is dry processing, getting rid of this altogether. Ideally, if you can make thicker electrodes, then you need fewer electrodes, fewer dead weight. Okay? But we do need materials that are better conductors. Remember, lithium ions have to move in and out fast. Electrons have to move in and out fast, so we have to improve both of those. And our NSF engine is starting to address this. I just came back from the University of Warwick in England, which is one of our partners in that we have an MOU there. Their campus is unique. They have what's called a Warwick Manufacturing Group. That's the largest school on the campus. It's totally in manufacturing, and I'm not sure if I know of any other college in the US or Europe that does the same thing. But it's in perspective, I got an honorary degree there a year ago. About 160 BS physics majors walked across the stage and a similar number of chemistry majors. The whole of New York State doesn't generate that many physics majors. They're doing something right, and we're going to try to find out exactly what they're doing. So the bottom line is we've got to get rid of this NMP. There's a lot of fluoride in batteries. We have to get rid of that to solve the PFAS problem, and we've got to lower the energy. So we look at the whole circular economy here, from the mine to making the materials, then making the cells. Lithium batteries have a lot of system management in them, a lot of electronics there to make sure you don't overcharge or over-discharge, and that all the cells are balanced. Absolutely critical for safety. Then there's various applications. Then hopefully recycle everything. So in the end, you don't have to mine anymore. And Apple has announced, I think, last year, they don't use any new cobalt in any of their products. It's all recycled cobalt. So this is what we're trying to solve. And we applied for this, what's called Build Back Better Regional Challenge. This came after COVID, to try to rebuild parts of the country that suffered the most. For those of you who don't know, Broome County, Binghamton, where I am, that was the original home of IBM. That's where they started out. About 8 years ago, they closed down, about 10,000 people lost their jobs. It was also the largest shoe manufacturing town in the whole of the US. For World War I, World War II, then all those jobs went overseas. And if you know anything about flight simulators, they all started in Binghamton as well, and that business has gone away. So there's essentially no manufacturing left in Binghamton, or for that matter in the Rochester area. So our goal was to try to address that. So we got money to build this battery prototyping center, which will be the largest in the US. Big issue, where do you get all this stuff from to make it? And we have a small gigafactory in town. You need about 250 different suppliers to make a lithium-ion battery pack. So we have New York BEST, which is a battery consortium addressing that. And the big issue when we talk to industry, we have no workers. No one knows how to make batteries. Even worse, we have no power electrical engineers. We don't train them anymore. So how do you fit all these things together and make sure they work? So we've got efforts working on that. We're trying to get the local community involved as much as we can, because they're the ones we're going to get the workers from and revamp it. Then we need the startup companies, universities, to come up with the new ideas and concepts. So that's where we got our money from. And this was the first of 3 awards we got. This is the Economic Development Administration, plus New York State gave us $50 million in matching within that. So you all know about valleys of death. You probably all know of one. There's in fact 3 according to the Department of Energy. The first one we know about is the typical technology one. You have an idea, does it work? Can you make it work? Then the second one is, can you commercialize it? And if you commercialize it, and the last one is, can you make any money? You can commercialize it, you can lose money year after year. It won't make it. So we have these three valleys of death. So we now have 3 programs to address these. We have the NSF engine, which is coming up for renewal, which is mostly addressing the first one, but then our renewal is moving across here because we can't make it sustainable, just the first one. Then the Build Back Better is addressing the commercialization area. Then we are designated as an EDA hub as well. We're hoping to get money from that one if the government issues the RFP. So we have these 3. For those of you who know about TRL levels, the NSF's at a very low one. The hub is getting to TRLs 8 to 9, and then we're hoping to get into the manufacturing end as well. So I showed you the circular economy. We've got now industry partners in each one of these segments. And I've got to say, these change month by month. As one company goes bankrupt and another one takes over, and things change. So on the mining effort, we got ICL, which used to mean Israel Chemical Limited, I think. They're now in the Midwest. Their research labs are in New York. They're going to manufacture lithium iron phosphate. It turns out Lee Industries, who's in Charlotte, is also now going to make LFP. They were a recycling company. They got $50 million from the feds for recycling. The feds said, we'd like you to make the fresh material too. You can feed your recycling in, but make the fresh. Company you're all familiar with, Kodak? Up in Rochester, a lot of spare space up there. They used to make photographic film, thermal film, exactly the same process you make to make battery electrodes. So they're booked out 6 to 9 months ahead to make electrodes for startup and larger companies. Then we have C4V, a R&D company, who is making cells and testing them. Then in the western part of the state, we have Electrovaya, which is building a gigafactory there. They are a Canadian company who's moved, and they've got money from the Export-Import Bank to build that facility. Okay. Then Viridi is a company in Buffalo. They make now large storage containers, mobile ones. Extremely interesting company. About 2/3 of their workforce lives within walking distance of their facility. More than half those workers are ex-prisoners. And most of those workers have been working for them for more than a year. So they've got loyal workers, they've worked very well. So that's now being used as a model for the rest of the state. I've already mentioned Toyota forklifts as an end user. BAE Systems are now getting into electric propulsion for aircraft as well. Then we have our local utility, NiMnCoAl, who it turns out is 100 feet from my lab. Most people don't realize it. That's their control center for the entire New York State and for parts of Canada. Then recycling, we have a gap there because Li-Cycle, who was in Rochester, has gone bankrupt twice now. So we think they've gone. But equally important, we have manufacturing, safety testing, both at RIT, Rochester Technology, and at Binghamton, and commercially at Intertech. And just 30 miles away, just across the border in Pennsylvania, we have Delta Modtech, who makes the machines for making the batteries. So we have a local company. There again, they used to make the machines for paper. They just switched over to batteries. Then we have for New York BEST, which is a consortium initiated by a governor back in about 2009, who decided New York State was going to be the center of the battery industry. He announced it in the State of the Union address. 2 hours later, we got a phone call. What are batteries and what's this all about? He never told us anything. So we went down the next week to staff, and that formed this New York BEST organization, which was supported for about 5 years. It's now totally self-supporting. And I have to emphasize, you can't do any of this without your political help. And we've had a champion until last November down in Washington, and this is Chuck Schumer, who came in. He embarrassed us on this occasion on one that he normally comes in suits and ties. This time he came in without the tie. Another time he came in with a sweater. So he's been a serious champion of ours and pushing as hard as he can to bring these activities to New York. So for my last slide, this is what we're building. This was an old Gannett printing press. They used it only for about 3 or 4 years. And before they decided to stop printing papers. The last time it was seriously used was in 2020. It was a state vaccination center for COVID. So right now we have the whole warehouse part at the back of this building where we're putting the prototyping facility in. There'll be 2 30-megawatt-hour lines in there, one for making flat pouch cells, one for making cylindrical cells, And this will be unique in the US. There's nowhere near this size. Right now, if a company, whether it's a startup or a large one, wants to make 1,000 cells for evaluation, you know where they go to make those 1,000 cells. Then your technology is gone. So this is being built right now. We have our leadership team on board, and this is Paul Maliband, who's the executive director, who I poached from Warwick in England. So the method to poach people, you get up there and say, we have this position we're looking for. Within half an hour after finishing my talk, somebody said, there's somebody who wants to talk to you. He was leading their effort, and he says, I'm interested. So we had to get him all the visas and things, but he's now on board, and he's securely on board because Wednesday last week, he bought his house. Okay, so the real interest, this is going to enhance national security, both jobs, and clearly the military are very interested in this. The military uses less than 1 gigawatt hour of batteries each year. Most of the small batteries still come from China. So even this prototyping facility can make most of the batteries if they demanded it for them. The real interest right now is clearly grid resiliency. And if any of you have looked at the business press, Texas is installing more energy storage than California this year. About 2 months ago, the batteries in Texas were supplying 16% or more of their energy when some of the big gas plants went down. So a very red state. The cattle ranchers like it. It's much easier work, and they make more money from solar, wind, and storage than they ever did by rustling cattle. So it's an exciting time for them. And clearly, it improves the health of everybody. And what we really want to do is enhance the workforce. But I keep warning my politicians, a gigafactory does not hire many people. They tend to be high-end people. If you go to China, CATL, the world's largest manufacturer, they have what they call dark factories. When the plant is running, there's no lights. There's no people on the manufacturing floor. There's 2 or 3 people behind computer screens watching things so they can send somebody in if things go wrong. But we work very closely with the major universities in the state. So that's Rochester, Syracuse, Cornell, the whole SUNY system. And then I said we have the business consortium. We work closely with those folks. So this is really where we're fully going. About a year from now, this should be up and running. Definitely has to be running before Christmas next year, okay? And right now we can make small cells, but our goal here is to make batteries in America by Americans, not in America by foreign countries. Our goal is to build them. You all saw the issues with South Korea. Just a week ago, they bring all their workers in from South Korea, even for the bulldozers. It's totally inappropriate. So we want to have these so they're run and operated by folks from here. So I will stop there. I'll try to answer any questions you might have. Thank you.
All right, the floor is open for questions.
Yeah.
There's a microphone coming your way.
Thank you. So electric vehicles, lithium ion, I know that's being used quite extensively. The issues that I have witnessed, for example, the Nissan Aria, if it's minus 13 degrees Fahrenheit, the entire battery freezes up and it's inoperative. The other issue is when we get a very cold spell up in the Northeast, and let's say it's 5 degrees Fahrenheit instead of 32 degrees, the range on the electric vehicle could actually decrease by 20 to 25%. My question is, what are you or your colleagues doing in order to remedy this type of issue? Because it's significant, especially in this part of the country.
So the country with the highest penetration of electric vehicles is Norway. Much colder than New Jersey, New York. They've solved it. I still remember in the old days when I used to drive to Exxon, On a cold morning, my colleague had called me, can you pick me up? My Mercedes diesel won't start, it's too cold. So now you basically have heater blocks in the engine. Same thing with batteries. If it's cold, you're going to have a heater to keep it running. The issue why they get less range when it's cold, because you turn on the heater, you turn on the windshield defogger, that all comes off the battery, internal combustion engine, that comes from the waste heat. So they use roughly energy.
Okay, but why exactly at minus 13 degrees Fahrenheit? For example, this Nissan Aria,
Right.
it's just totally it's inoperable.
Yeah.
Is there anything that you could do? Well, not you personally, but
Right.
anything that can be done to prevent this from
Right.
occurring? Any kind of special chemistry?
Right. So the reason for that is the electrolyte used in there gets too viscous to conduct ions. It's the same issue you get in most systems. Some of you may remember the 787 had some smoking, fire issues. Each one of those was after the plane being parked outside in freezing weather, and they turned on in the morning and boiled the electrolyte. So we wanted to operate cold. We're going to have to change the electrolyte. And it turns out we have a contract right now through the University of Maryland from the military to design batteries that will work under what they call extreme conditions. They're talking about minus 30 Fahrenheit, minus 40 Fahrenheit.
Okay. Thank you.
Thank you very much. It was just wonderfully rich, packed with information like, the batteries are packed with charge carriers. I'm wondering if you can comment on the evolution of the interplay between within the development of the batteries of experiments at one limit, an Edisonian approach, and how the development has changed with validated computing over, say, the last 25 years or so. How has the role of computing changed in the development of your future targets?
Okay. So for those who are not familiar with 1970s, computers, they didn't really exist. You couldn't do any of your calculations. When I was at Stanford, I got one of HP's first little calculators. It was $350. When I finally moved to Schlumberger after Exxon, they had a Cray computer, which could do the big calculations, but didn't do the little things. It turns out it worked very nicely with small Macs. It didn't like the DOS system, so we used that. But basically, we did no computing. If you're a graduate student, you got a PhD thesis on solving one crystal structure. So in those days, it was all chemical intuition. Today, we certainly use theoretical calculations. I would say more to guide the experimentalist if you've got 3 or 4 different options, which is the most promising. But I have to say, despite what some others have said in the literature, no one has predicted a new battery material using computational science. They've given us some clues and come up with some nice cathodes, but when we take the lithium out of those cathodes, it goes puff into a gas. So it is not helpful. But no, the interesting thing now, I think, is more, what can AI do? What can it teach us from what's gone before? To put in perspective how important that is, CATL, we're told, has between 1,000 and 2,000 engineers working on AI and machine learning. We're going to be doing some of that. Again, it's really to guide us. What have we learned in the past? Where should we go in the future? But chemists and others are always going to have a job. Chemical intuition, just like female intuition, rules the waves. Okay.
First of all, very interesting presentation. And as NiMnCoAl said at the beginning, thanks for making the modern life possible with the invention of the lithium-ion batteries. My question is that there's explosion in the use of electric cars and all of that. There is a life to these batteries.
Yes.
10 years from now, 15 years from now, what are we going to do with all of these old batteries? And what is the solution for
Okay. So,
disposing them?
yeah, we're not going to dispose of them. There's too much valuable stuff inside. So I don't know what the law in New Jersey is. In New York State, it's illegal to throw any battery, teeny weeny one or a huge one, into the garbage. So that they will all get recycled. The real challenge now, we can use brute force and ignorance to recycle it, which means take the batteries out. We cook them to a high temperature, which gets rid of the organics. Then we have what's called black mass, which is a mixture of all the metals. The challenge is how do we separate those metals in a economically viable way? And a lot of the companies are saying that black mass to Asia to do it. If you've got federal funding, you are not allowed to do that. So some of that is building up here. We need economic methods of separating that out. Or what I know, think we need smarter ways of making batteries and recovering the materials from the batteries without destroying them. Because remember, you've got a battery, you've got solder, all sorts of things. So if you destroy the battery, which is what they basically grind them up now, all of that gets into this black mass. And Apple, I know, can take all their electrodes apart and take the active material off them. And we have to look at approaches like that, whether solvents can dissolve it off, or we use different binders than we use today. We use fluorine-based binders today, which is very difficult to remove. If we can get a binder that's soluble in water, then we can just put these electrodes in water, dissolve off all the material you want, and then recover the nickel, cobalt, and so on. There's going to be a lot of effort there. The government is trying to do something. It's not easy, but it's doable. We just have to put some money. And Argonne, I know, has a leading program in that area. I haven't heard anything really great coming from it yet. But for the US, the largest material for recycling is manufacturing waste. When you start a new gigafactory, maybe 80% of the stuff you make is garbage. When it's working well, in most countries, you're above 95%. At CATL, they're about 99% because of all this AI they're doing. But we have to find a way of recovering all those valuable metals.
Thank you so much. I remember you mentioned something like lithium's biggest problem is that as they grow, they crack. So is something like vapor deposition or any type of other deposition technique possible with lithium, or is it just not feasible?
No. The reason it cracks, these materials expand and contract about 10% when you charge and discharge. So you've got these meatballs, you've got some particles this way, some this way. So they will tend to crack if they're against each other. If they're single crystals, they tend not to crack. So it's not how you make them, it's their own morphology and that causes the cracking. So we think if we keep them small enough, we paint them, we can stop the cracking.
All right, so we are not looking to build bigger crystals. We are looking to build smaller but more stable crystals.
We want crystals about 3 microns in size, not too small. But if we get bigger than that, those crystals will crack. And we studied this at length at Exxon when we had these large crystals. We could actually look at them under an optical microscope as we put lithium in and seeing the cracks forming.
Thank you.
So yes, I am a proud owner of a Trek electric bicycle. The battery, it's a lithium-ion battery. It's manufactured in Poland. I have the German drivetrain on it. What I was looking for in an electric bicycle was the UL listing, Underwriters Laboratories. What is the criteria for a battery to be so-called approved by UL?
There's a whole set of tests they have to pass, and they can cost hundreds of thousands of dollars to do them. It's illegal to sell or buy a battery or a charging system in New York City if it's not UL approved. The firefighters can come in and take all your products away. So it's being addressed. We're having the same issue building our facility. Will the European equivalent be okay? The people say, yeah, we want UL, please. We had one last question here, I think. Okay.
For the great talk. So I want to ask a question about workforce. So since battery making is a work of art, it's not that easy to do so. We would like to, foster the future workforce. What kind of preparedness should be? How can we prepare the future workforce, and especially for us, Innovation Technology University, to contribute that aspect?
There's several answers. One, if you've got 6 students in the group, 1 or 2 of them will have a green thumb, and they can make beautiful batteries. Some of the others can't do it to save their lives. But no, my comments, and I get myself in trouble for this all the time. We taught the Asians how to make batteries initially. We have to reduce our pride and bring in CATL into this country and learn from them how we make batteries. And I know the federal government said they're not coming in. At least 2 states, maybe California and New York, would let them in. I don't know what New Jersey's political situation is, but we have to learn from the best. There's no way we can catch up with what they're doing. We have to leapfrog that doing, but take their best practices.
Yeah. Thank you for the presentation. I kind of had a 2-part question. One was, you mentioned like localized supply chains. So what does that look like for each, I guess, continent? And then the second one is, there's a lot of like ethics issues with like mining, or you mentioned like PFAS. Do you know what the future of that looks like? Is your group investing any time on that?
So the issue is mostly cobalt. It's child labor in Congo, and it's Chinese who are driving that to some extent. So the goal here is to eliminate, if we can, all the cobalt. I think the rest of the world's doing that. Nickel we have in Canada. We have some elements in this country, but we have lithium mines in North Carolina, which were used. To get them reactivated will take 10 years. If you want to start a new mine, it's 20 years. So I think one of the past senators from West Virginia says we have to do something about expediting these rules, because it's not just the mining. We can make far more wind power in upstate New York next to the lakes. We can't get that wind down to New Jersey and New York City because they won't let us put bigger power lines in. So we have to get over a lot of these hurdles that are presenting us. We've got to move much, much faster than we do today. And your president gave me a beautiful example of how he can move much faster here than in a state-run university. So we need to get some of the bureaucracy out of the way so we can, in fact, charge ahead. We can't remain with the status quo. We've got all the iron we need to make lithium iron phosphate here. We can fight with the farmers for the phosphorus. We got the oxygen. We can make those batteries in this country. And the tons and tons of lithium in South America. And we talk to the South Americans and tell them, stop shipping the ore to China and elsewhere. Work on it in your own country, upgrade it, and keep most of the money in your country. Don't just give it away, which is what a lot of these countries are doing.
Dr. Whittingham, can I take this microphone?
Yeah.
Well, first of all, I want to thank you again. But would it be possible for me to use my prerogative to ask you a couple of questions?
Of course.
Thank you so much. First question is very simple. We had a brief conversation before your lecture, and we agreed that the price of about 1 kilowatt hour of battery in this country is north of $100.
Yes.
And in China, it's about 1/2 of that. And we agreed that if the price in the United States were to go down by that much, the impact on the economy is tremendous. Right. So can you tell us why it is that the Chinese can sell their batteries for so much less?
First, obviously they get state funding, not directly. No. What they get is dorms for the workers built, they get the land free, they get the highways built for free. And what we're now learning from China is the local provinces are competing with each other. So the provinces are in fact subsidizing it. So the Chinese are not actually making any money at $35. We think $60 is probably break even. And in this country, right now, unless things change, if you make a 1 kilowatt hour battery, the federal government will pay the manufacturer $35 to $40 per kilowatt hour as a kind of incentive. So we can do it, we should be able to do it, but I say we got to know how to make batteries, and we got to know how to make it in a very automated fashion. If you see, just looking at old cars, looking at how Detroit makes cars, look at the Chinese factory. Again, there's no one there on the floor. It's all robots doing everything.
I have a second question. You've been working in this business for a lifetime, a long time. And your contributions from many, many years ago led to a Nobel Prize. It led to actually the first functional lithium battery, and you continue to work. So you know a lot about what's happening in this area. So use all this experience and knowledge and give us your prediction. Where will battery technology be 10 years from now?
I think I can safely say we'll still be using lithium because there's two reasons. One, it has the highest energy density. The second one, the price is low. It'll be very difficult for anything else to compete. But the energy density of those cells will go from 250 today to about 350 to 400 in small cells as well as the large ones. And they'll be in most vehicles. I heard an extremely impressive talk last week from a British guy who works for an Australian mining company. Those big trucks that carry maybe 200 tons of ore, they're converting them all over to EV vehicles. They have 3 megawatt hours of batteries. That's more than one container on each one of those trucks. And he said, you stand next to a truck, his head came up to about the axle on the truck. So these trucks are huge. So it's moving into that area. It's going to move into every area. And I think the cost is going to come down. I'm hoping my watch will last more than one day. It runs out before I can plug it in at night. We'd like them all to last longer. And it's something you can all understand, so you can all champion it and talk to your politicians. But this is incredibly important for the US. Germany is probably the country panicking the most right now. About 15 to 18% of the population is in the car industry.
Automotive, yeah.
So if the Chinese take over the batteries, those people have no jobs.
Yep. Well, what can I say? This was a fascinating, outstanding, informative talk. So may I ask all of you to join me in thanking Dr. Whittingham. Now, we have a little ritual here. I don't know if you're aware of this, but if you're not, I'm happy to surprise you. At this time, I am pleased to confer the 10th President's Medal upon Dr. Whittingham. The President's Medal is awarded to individuals who've had a significant impact on society by virtue of their science and technology-focused research and development activities and contributions, their leadership in business education or the public sector, their artistic or cultural contributions, or their success in elucidating critical topics for greater public understanding, policymaking, and action. Today, I bestow upon Dr. Whittingham for his leadership and significant contributions to the field of energy, the President's Medal. So, Dr. Whittingham, with your permission, since we have a photographer on hand, I'm going to, without trying to hurt you, I'll put this around your neck. Yeah. Where is Jeff? Jeff is here. Yeah, if we can go up front.
Don't go too far over.
Is this good? If you would come here, please.
Yep.
And I'm going to try and put this on you. Congratulations.
Thank you.
Thank you. And by the way, there's a nice box here. And in addition, as further tribute to Dr. Whittingham's influence, a deserving and talented incoming first-year student will be selected to receive a scholarship named in his honor next fall. So we will be sure to keep in touch with you to let you know who the student, the lucky student recipient of your scholarship will be, and maybe we'll make an arrangement for you to meet with the student. We are really delighted for everything that you've done today. I want to thank you again for sharing your insights as part of the President's Distinguished Lecture Series, and invite you and all the audience to join me at a reception which I believe is being held upstairs in the same building, in the gallery room. There you will have an opportunity to say hello to Dr. Whittingham. And if there are any other questions that you haven't had the chance to ask, that would be your opportunity. Thank you again.
Thank you.
Thank you very much.
Thank you.